So in this video, what we're going to do is we're going to talk about how to draw the molecular orbital diagram for hydroxide, right, for HO minus. In this case right here, right, so it's a heteronuclear diatomic, so you have two different types of atoms that are going to be combining together to form a single molecule, right, and we can draw the MO diagram for that. So the way that we approach this, right, I mean, we can just draw out what the structure looks like, right, using what we know about Lewis structures, right, so it looks like this right here, single bond between the hydrogen and the oxygen, right, and the oxygen has an extra negative charge. Now, when drawing out the MO diagram, right, the approach that you should use, you should put the two different atoms for on opposite sides of your page. So I'm going to have the hydrogen over here, right? And so I know that the hydrogen is probably going to be pretty high up in energy, and it only has the 1s orbital, so I'm going to put the 1s up here. And then over here, right, I'm going to have my oxygen, and I'm going to, make this just simply O minus, right? I'm going to say that this is where that, extra negative charge is going to be located, and I know that oxygen is a more electronegative atom than hydrogen. And so in that case, I would expect the orbitals for oxygen to be lower in energy compared to the hydrogen, right? So I would expect then my 2s to be somewhere down here, and then I would have my 2p's over here, in this case right here. So, right, so the bare bone stuff is in there. Now I'm just going to, draw out my put in the electrons, right? So in the case of hydrogen, we have one electron here. In the case of oxygen, right, with one extra electron in this instance, right, we have a total of 7 electrons then. So we get something that looks like this right here, right? And so that's what the atomic orbital diagrams look like for both of these atoms/ions. So now when we're drawing the MO, right, the MO should be drawn in the middle between the two of them, right? So that should be HO minus. Now the thing to point out, right, because the 1s is just so much higher in energy than the 2p and the 2s, the 1s is really only going to interact with the one orbital on the 2p that it can actually form a molecular orbital with, right? So if we look at it right here, right, the 2s, right, has the right shape, right, in both of these cases, but the 2s is just so far down. The one that's actually closest in energy is going to be the 2p. And so there's, 1, 2, 3, p orbitals, right? There's the pz, the px, and the py in these cases. And so if we're looking at it, there's only one orbital that the 1s can really interact with, right? Because it has the right shape. It's the, the p orbital that's actually going to be pointed towards the 1s orbital. And so what's going to happen now when we're drawing out our MO diagram is that we're going to have one orbital that sits all the way down here at the bottom, right? So this 2s isn't going to change in energy, right? We would assume that to stay exactly the same, and we would refer this to as being a non-bonding orbital, right? So I just simply signify that as NB. And so that's just going to tell us that that orbital, that molecular orbital, right, is actually not a bonding orbital, right? It's just simply, a set of orbitals that are just hanging out, so to say. Now next, right, when we combine, the 1s then with one of the 2p orbitals, right, the one that it combines with, we would end up forming then a sigma bonding orbital in this instance, right? And so if we're forming a sigma bonding orbital, right, the sigma bonding orbital is going to be lower in energy than the lowest energy atomic orbital, right? So in this case, right, the 2p is lower in energy, so we would expect the sigma bonding orbital to be lower than that. So I'm just going to draw that right here, right? So this is going to be the sigma bonding orbital between the 2p and the 1s. And then similarly, right, if we have a sigma bonding orbital, we have to draw a sigma anti-bonding orbital. That will then be higher in energy than the highest energy atomic orbital that's participating in this bonding, right? So that means that in this case, the sigma anti-bonding orbital is going to have to be higher than the 1s orbital on the hydrogen, right? So that's going to be somewhere up here then. So that's going to be the sigma star, right, anti-bonding, and so that's again coming from the 1s in both of these cases. Now, one important thing to point out is that you have to have the same number of molecular orbitals as atomic orbitals that are participating, right? So in this case right here, if we're looking at it, the hydrogen atom is contributing 1 electron in this case, or so not 1 electron, sorry, 1 orbital, whereas over here in the case of the O minus, right, that's contributing 4 orbitals. So that means that we have to have a total of 5 orbitals for the MOs, right, for the molecular orbitals in this case, right, because there's a total of 5 atomic orbitals that are participating. There's going to be 5 MOs that have to get formed. So right now, right, we already have one non-bonding orbital because of the 2s. We have a sigma bonding orbital that's a combination of the 1s with one of the 2p orbitals, and then we have then also the sigma anti-bonding orbital. The other two 2p orbitals on that oxygen, because they're perpendicular to essentially the location of the 1s, right, they actually form what are referred to as non-bonding orbitals as well. And so in these instances, right, you're going to then have 2 orbitals that aren't going to change in energy, right? They're going to stay at the exact same energy that they started off with. In this case, right, they're both going to be non-bonding orbitals. So if I were to just simply draw out, right, what this looks like, right, this is a combination where I have, you know, the 1s over here, right, and then this is a 2p in this case, and then this guy right here is then just simply going to be the anti-bonding combination right there. These guys, right, are going to be attempts, right, where you have your 1s, but because the shape and direction of the orbitals don't match, you know, to actually interact and overlap with the 1s, those become non-bonding orbitals in that case, right? And so they're non-bonding, they're not interacting with the bonding. You don't add them up when you're doing any kind of math for bond orders or anything, right? They get disregarded in that case. You don't change the energy of them, right? They stay at the exact same energy that they had started off with. As you know, atomic orbitals, because they're still basically atomic orbitals, right? They're not interacting with anything. So, you know, that's the reason why, right? That's how you approach that right there. Now, we essentially, right, we have our framework for molecular orbital diagram right here. So I'm just going to delete these lines right here. So now all we have to do is we have to add up how many electrons we're actually going to be contributing and being put into the molecular orbital diagram. So in the case of the hydrogen, right, it only has 1 electron. In the case of the O-, right, we have 7 electrons. So there's a total of 8 electrons that we should be putting into our molecular orbital diagram. Now, following, right, the Aufbau principle, Hund's rule, and the Pauli exclusion principle, right, we should be able to fill in, you know, our molecular orbital diagram with these electrons, right, and get an understanding of what the bonding looks like. So if we go in, right, we have a total of 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. Right? So we have 8 electrons in this case right here, and so we can see that the non-bonding orbitals are going to be completely filled, but the sigma anti-bonding orbital is going to be completely empty. And so, you know, if we were to calculate out the bond order in this case, right, the equation for bond order is you add up the number of electrons that are in bonding orbitals. So in our instance, right, that's only 2. And then you subtract out the number of electrons that are in anti-bonding orbitals. And so in this case right here, right, that's going to be 0 because we don't have any in the anti-bonding orbitals. We do have 6 in non-bonding orbitals, but because they don't contribute to the bond at all, right, they get completely disregarded in this equation. So we don't have to worry about them. And so once you have that right there, right, you just divide that by 2. 2 minus 0 is 2. 2 divided by 2 gives you 1, right? So you have a bond order of 1, which matches our Lewis structure in this case right here. And so, you know, that's the way that you approach this and think about, you know, how to do these types of, you know, molecular orbital diagrams for a heteronuclear diatomic, where you have extra electrons, right? So we're working with something that's an anion, so there's an extra electron that's included, but also one where you don't have only sigma bonding or sigma or pi bonding combinations, right? This one included non-bonding combinations, and you have to think about the symmetry and how far away in energy things are to figure out if you even are going to get any kind of non-bonding orbitals in these cases. So that's how you approach this problem.